Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today in this tutorial I will explain the paper Federated Learning for Keyword Spotting. This paper was published into archive last month and the recent version of this paper was submitted this month 18th. This paper is by a company called Snips from Paris and the tutorial is going to cover the overview of the paper. Then we'll explain what is federated learning. Then we'll see what is federated optimization, which is used in this paper. Then we'll see what is the data set they have used in this paper to conduct the experiments. Then we'll see the experiments and finally we'll see some results on that experiments. So the overview is this paper does something called keyword spotting, which is basically recognizing a particular keyword from the audio stream. Then this paper introduces how we can do federated learning or decentralized training for the keyword spotting task. Then this paper introduces a new dataset called new dataset, which is for keyword spotting community, which has the keywords hey snips, just like we have Hey Siri or OK Google. And this the paper studies this keyword spotting using federated learning algorithm, and the keyword used here is Hey Snips, just like OK Google and Hey Siri. Then they also show that using adaptive averaging strategy highly reduces the number of communication rounds we require for achieving the target performance. Then this paper uses federated averaging algorithm for training the keyword spotting model. So first we'll see what is federated learning. So federated learning is also, you can think of it as decentralized training. So what we are doing or going to do here is, unlike any other training mechanism we have today, for example, if you want to train a ImageNet classifier, what we do is we buy a server which has GPU, and we put all the data in the server, and we write a training script and we train the model within that server. But what this decentralized training or federated learning does is it tries to use lot of small devices which are available, for example mobile devices. So we can think of each mobile devices as a training server. It's not a server, you can think of it as a small compute node which we have. So a lot of people will have mobile phones. So what this federated learning does is it tries to use all the mobile phones or all the devices which are not connected to each other, and tries to train a model using this strategy. For example, let's say we have hundreds of phones, mobile phones used by hundreds of people. Then this federated learning algorithm basically takes a model which is, for example, the model which is, for example, at a time t we have some model which can have some performance, which is denoted with blue here. Then it sends all this model to all the mobile phones available in that in that cluster, for example. Then each phone takes this model, and they will have their own training data assigned to them, and they train the model within this phone, and that will be done, the same thing will be done by hundreds of mobile phones, for example. Then after each mobile phone trains their own model, they send each phone sends their own model to something called parameter server, which is denoted with blue here. So each mobile phone after training sends this blue model, and there is a parameter server in the cloud which takes all these blue models and tries to update its own master model, which is going to be sent back to these mobile phones again for the next iteration. So basically in deep learning or in machine learning, we will have some model and we want to train this model in iterative fashion. For example, let's say at time t we have this blue model. Once all the mobile phones trains their own model with their own data, then we update the master model which is sitting at somewhere in the cloud, which actually takes all the small models built by, or all the small models trained by these mobile phones, and tries to average all these models and create a new model which is going to be distributed back to these mobile phones again. So this is called federated learning or decentralized learning. What is centralized learning? Centralized learning is basically you have a cluster or a data center where all the machines are connected together already through InfiniBand or through LAN cable or with this new NVLink kind of GPU cables. So all the systems are connected together, and we can distribute the data, or we can train a distributed model using our data. And each model, and there are many strategies to doing that, but this sort of decentralized training or federated learning is started recently, right? For example, the Gboard we use in our mobile phone, basically Google has a federated learning algorithm running behind it. So this is federated learning, and there is an algorithm called federated averaging. So basically what is federated averaging, we'll come to that, but what we do in federated averaging or federated optimization technique is, let's say we have a function f which has a parameter, or which let's say we have a learning objective. Basically is a loss function which takes xi, which is the training input, and which is a data point, and yi is the label, and w is the parameters of that network, and that's a function fi. So this loss function L takes pair of data and it has a weight. So and you can assume each the W, which is the weight, as a dimension D. So what we do is, these data points I are, we are going to partition these data points into k cluster or k user. For example, let's say we take 100 images and we distribute into 10 different users. So each one will take 10 images, and they are going to so we call that a partition. So basically k users, each being assigned with their own partition pk, and the number of points within that pk, which is the number of data points assigned to one person, basically, or kth user, is basically nk. Now our objective is to minimize the loss, which is minimizing this fi of w, which is this nothing but a loss function. So how do we optimize? Because now the data points are distributed, and the loss function we have to compute using all the data, not with a small amount of data. So we have, let's say, 100 data points, and we have already distributed 10 data points to 10 people. And now how do we optimize this loss function? So basically what we do is in order to minimize this f, which is the loss function, we say we are going to create an function fk, is capital Fk. So basically capital Fk is the objective function optimized at the kth person or kth user, okay, which will have who has same parameter w, right? And fk, for example, if k equal to 1 corresponds to the first user, and f2 of w corresponds to the second user. So that way we have a lot of or multiple objective functions here. So capital F small k basically corresponds to objective function at corresponding user k. So if you have capital K number of user, or capital K number of user, then we have to somehow average this loss function over all the users. So what we are going to do is, we are going to scale this objective function by this ratio nk by n. Basically nk is the number of data points assigned to that user, and capital N is the total number of data points, and we are going to sum this objective function over all the users, right? And basically this capital Fk of w is nothing but computing the loss function at every data point. For example, if kth user is assigned with nk number of data points, we have to get the final loss, which is going to be the average of all the loss for that cluster, or all the for that partition. So if you have 10 data points, we get 10 different loss values, and we average it, and we get one loss value, which is what is done in deep neural network training or any other training. This is federated optimization, and this is general case where we have xi and yi is basically a pair of data which has input and the label, and we have a model which has a weight parameters w. Now how do we use this for keyword spotting? So I will come to keyword spotting next. This is the federated optimization technique. So basically, there are few steps in federated optimization. I'll go through each one of them. Basically, if we at a time t minus 1, we'll have a model which has the weights w t minus 1. So we are going to share this model with subset of users. So as I said, capital K number of users. Let's assume here at a time t we are submitting to st number of users, because the number of users at every time may change. So we randomly select st number of users from pool of k users. Then, so small k basically belongs to one of the user in the pool st, or randomly selected subset. So what we do is we send our model, which has the weights w t minus 1. I mean, we send the model and the local data, and we minimize that objective function using stochastic gradient descent, and they will have their own learning rate, which we call it as eta local. Then the users from st, which is nothing but the number of users which you have randomly selected from pool of k user, basically send their model updates back to this parameter server. So basically, after they do the training, we are going to get a new parameters wtk. So wt stands for we are looking at the weights at time t, and k is the index of that user. For example, if you have 10 user, we get 10 different weights. Okay, then we average it. We'll see how we are going to average it. We have a separate equation for it. I'll show you that. So this parameter server actually computes the average model wt based on each individual user updates, right? So how is it done? So the global averaging step, which is nothing but computing wt from wt minus 1, which is not a wt minus 1 is not a single weight function, which wt minus 1 basically the previous parameters. And how are we going to get wt is nothing but we have a previous model, and we have a global learning parameter, which is called eta global. Then each user, or each user sends their own parameter updates, or sends their own new parameters, which they get it after they train the model on their local device with the local data. So that you are going to update this new model with this equation. Okay, so this equation is, as you can see, the k is one of the index from the subset st, and we are going to sum this difference, which is going to be weighted by this number, and this is the global update which we are going to do to the model in the parameter server. Then what we do is we are going to send this back to all the mobile devices. So we might randomly again select st number of users from the k number of users. Then we send this model back to other mobile phones with the data, and then they will going to do the training, and this process repeats. This is the whole idea. And however, what the paper name actually says Federated Learning for Keyword Spotting, right? So what we understood till now is just a federated learning. Then what is keyword spotting? So basically, keyword spotting is nothing but identifying a specific keyword in the audio stream. For example, I am speaking something right now, but if you are interested in listening to a word which you are interested in, for example, I might mention the name Jan Lekun. And if you are looking for a word Jan Lekun, then our keyword spotting system should be able to detect at what point in time this word Jan Lekun came in this audio stream, right? So the same thing happens with Google Voice also. If I say OK Google to my phone, it wakes up, which is called wake word recognition, which is again something similar to keyword spotting. Or if you are using a Alexa, Amazon's Alexa, you say Alexa, then the Alexa speech recognition engine wakes up and it listens to what you are going to see after you say Alexa, and it does the job. I mean, it does whatever task you ask it to do. So that is wake word recognition, or it's also called keyword spotting. Sometimes people say wake word recognition not exactly similar to keyword spotting, because keyword spotting you can apply it on data which is already there in your database and to search for a keyword. But wake word recognition basically is about finding out the keyword in the audio stream which you are streaming, live stream, for example. Like for example, now Google may be listening to me. As soon as I say OK Google, it's going to wake up. So the OK Google is actually a keyword for this Google's keyword spotting algorithm. Right? In the same way, these guys wanted to build this sort of federated learning algorithm for a keyword called hey snips. So basically, Snips is the company name, which is located in Paris, I believe, France, I think. And Hey Snips basically is a keyword just like OK Google or Hey Siri, right? And they have collected the data, and they have collected in such a way that collected it using crowdsourcing, so that the data distribution mimics the real world non IID constraint, because whatever data we are dealing with is also non IID. And I mean, the real world federated learning algorithm needs non IID data and balanced. And this is highly distributed setting. Why I am saying the highly distributed? Because we are using thousands of mobile phone, or even hundreds of thousands of mobile phones to do your training. This is completely decentralized. So, so this is the data which they have collected from crowdsource, and the statistics of the data is like this. So basically, they have 1,374 users. This is version 1 of the HeySnips dataset, which is available online. You can download it and use it for your own, like if you want to do research on the data, or if you want to build a keyword spotting algorithm, new algorithm, and you can use that as a baseline. So that data is open, you can use it. And the training data, they have around 1,374 user, and they have 53,000 returns. And total, I mean, dev, that is for training, and dev they have this much, and test they have this much. And so this is the data set. So basically, it's about the data which will be about the keyword hey snips. And since you during training, you don't want to only recognize, I mean, you are interested in recognizing hey snips, but you don't want to recognize any other keywords. So this setup, basically, I'll tell you how the setup is. So this is the keyword spotting task. And for experimentation, so what they are doing is they are building a convolutional neural network, which actually takes some spectrogram or MFCC sort of features and tries to predict 4 different things. So basically, they have 4 different neurons on the output. You can think of it as 4 different softmax output. So basically, one is dedicated to the word hey, and another neuron is dedicated to the subword sni, and another neuron is dedicated to subword ps, right? And the last neuron is basically a filler, and that can take that will take care of all the other words except these two hey snips words, right? So basically, when you're training, you will say whether this word is hey snips, really hey snip, or something else. So basically, we have 4 neurons, 3 of them are dedicated to hey snips, and 1 is for filler, which is a junk, or which can take any word. So the input to the network, convolutional neural network, is going to be 40-dimensional MFCC computed over 10 millisecond window. Computed over shift of 10 millisecond with 25 millisecond window, and they stack the frames 32. They stack 32 frames to the left and right context, and the CNN is built with stacked dilation convolution layers, and the output is 4 softmax layers. So the output layer is 4 softmax neurons, and as I said, the 4 neurons assigned 4 neurons belongs to the first one belongs to hey, and second one belongs to sni, third one belongs to sp, and fourth one is a filler. So the filler takes care of all the other cases other than hey snips. And one more thing is, since we are independently predicting for these segments, or independently predicting the posterior probabilities for every every 32 frames, we might have to do something called posterior smoothing, which was introduced in 2015 by Tara Sainath for the same problem, for OK Google keyword spotting problem, and they have used the same thing. They take posterior handling to generate a confidence score for every frame, and combining smooth labels posterior, and they finally say whether within this window this word occurred or not, or this K snip occurred or not. And they measure some and they set some threshold, and they say if the threshold goes beyond this, or if the number goes beyond this threshold, will say, or will trigger the system saying this OK Google or hey word a snip happened. And coming to the result, we have here they just show like how, I mean, with respect to the number of communication rounds, how the false alarm is going up, or false alarms, and the results or the accuracies Or like here, like if you use global average learning rate or global learning rate for the federated averaging update, then you will get after 100 round you get 29%, after 400 round you get 67.3%. But if you use Adams strategy with the learning rate of or global learning rate of 0.01 for federating averaging, then after 100 round you get 93, and after 400 you get 98.29. And this is all about this paper, federated learning for keyword spotting. And thank you for watching.